You think light travels in a straight line, like an arrow? Richard Feynman proved that's just an illusion. In reality, a beam of light doesn't even exist. Why is it that we just accept that light reflects off a mirror because it has to? Why does it always choose that exact shortest path we were forced to draw in high school textbooks? I've always found that question incredibly frustrating, not because the physics is too hard to grasp, but because the standard answers we're fed feel so hollow. People tell us that the angle of incidence must equal the angle of reflection, as if it is some cosmic commandment carved in stone. They show us these sterile, clean diagrams from 17th century optics and say, light behaves like a billiard ball bouncing off the cushion. But to me, that always felt like a bit of a cheat. It's like someone showing you a straight line on a graph and telling you nature is obligated to walk along it, simply because they drew it that way. And while I'm still trying to wrap my head around why the universe forces things to behave this way, I'm tired of hearing about dry geometric rules. I do not want more formulas that look pretty on a chalkboard but say nothing to my imagination. What I want to know is what is actually happening in the physical world in that split second when a photon travels from a light bulb to your bathroom mirror. What, in a very concrete way, at the very foundation of matter, is directing that motion? Because if this is a fundamental mechanism of our universe, it should be tied to how space, particles, and time itself truly operate, not just a lucky mathematical guess. And if we pause here and really let ourselves think about it, perhaps this simple question opens up a perspective that is absolutely breathtaking. To understand why light seems so incredibly smart, rock-solid, and disciplined, I think we should set aside the rulers and protractors for a moment. Let's look at it as simply as possible. It was 1948 when the physicist Richard Feynman introduced a concept that would form the basis of quantum electrodynamics. And while the math behind it is staggering, the core idea borders on pure madness. You see, a photon does not choose one correct PCM propers. In reality, it takes every possible path simultaneously. To visualize this, imagine you're expecting a package delivered from point A to point B. In our everyday world, the courier just gets in the truck and follows the GPS along the straightest road. But in the quantum world, our character is a completely mad, drunken courier with no sense of logic. To deliver a single photon, he simultaneously runs through your neighbor's yard, stops for coffee in another city, takes a massive detour around the moon, and somehow, miraculously, ends up at your front door. Feynman suggested we think about this using an imaginary stopwatch held by every one of these couriers. While the courier is in transit, the hand of that watch is spinning at a frantic speed. The moment he hits his target and reaches your eye, he freezes, and we look at where that hand is pointing, up, down, or sideways. In physics, we call this a probability vector. And the final result we see is simply the sum of all those stopwatch hands from every conceivable route. Now, let us bring that process into the scale of your bathroom. Imagine the cold, smooth surface of the mirror glass. When the light from the bulb hits it, the photon is actually striking every single atom of that glass, every microscopic scratch and speck of dust on the surface. From a quantum perspective, it's not just reflecting off the center of the mirror like we were taught in school. Our Mai Hatori, our mad courier, is simultaneously reflecting off the far left edge, the far right, the top corner, and even the decorative frame. And here is the critical moment. The paths that go through the edges of the mirror are physically longer. This means that while our courier was taking that extra detour, the hand on his internal stopwatch had time to make many more revolutions. When we try to add up the results from the edges of the mirror, the stopwatch hands point in completely different directions. One is up, one is down. In total, they simply cancel each other out. They delete one another. For your eye, the light from the edges of the mirror effectively does not exist. It has turned itself off. Think of it like a massive stadium where thousands of people are trying to sing the same song. If they're all sitting in different sections, singing out of sync, it's just a wall of unintelligible noise. Their voices drown each other out until it's just a hum. But at the center of the mirror, the situation is different. There, the paths are almost exactly the same length. The difference in distance is so tiny that the stopwatch hands of almost every courier reflecting off the center freeze in the same direction. They arrive at the finish line in sync, in step. Nay, their hands do not cancel each other out. Instead, they stack up, reinforcing the brightness like a choir that suddenly hits a perfect ringing unison. That powerful synchronized bass sound is what we call a beam of light. This leads us to a very uncomfortable, almost haunting conclusion. We see a reflection in the center of the mirror, not because light decided to hit that spot. It's because the center is the only place where all those possible paths manage to agree with each other. Every other billion-to-one option literally devoured itself, destroyed by the slightest desync in rhythm. It turns out that the reality we see in the mirror is not the full picture of the world at all. It's just a tiny fragment of a global chaos, the one surviving echo that managed to scream louder than the noise. We see order not because the world is simple and linear, but because everything else simply erased itself. If that is not magic hidden in the mundane, then what is? But what about the tools we actually use? The lenses in your glasses, the massive telescopes peering into deep space, the tiny cameras in our smartphones, surely they are not just masked versions of this quantum chaos. Many people expect that when we move from a simple mirror to sophisticated engineering, the rules must naturally change to something more solid. But when you break a real lens down to its fundamentals, you find it is not immune to this mad mechanism. In fact, it's the ultimate proof of it. Take a classic glass lens. On a macroscopic level, everything seems straightforward. You see rays of light bending and converging perfectly at a single point. It looks clean, logical, and intentional. But if we zoom into the atomic scale, we discover a reality that is far more taxing. We find that glass is actually an enormous pool filled with thick jello for light. No photon simply zips through it. Glass slows particles down, and this slowdown is not just an abstract number in a physics problem. It's a grueling physical process of passing energy from one atom to the next, like a bucket brigade where every handoff takes a fraction of a second. Your physics teacher spent years drawing neat little arrows on the chalkboard to explain refraction, but he never told you the real price light pays to pass through that glass. He never mentioned that behind that beautiful, effortless curve of the beam lies a total grind of deceleration and a ruthless battle of phases. Our intuition tricks us into thinking light simply turns, like a car at an intersection. But light does not turn because it wants to. It turns because it is being obstructed. What we see as a graceful bend is actually the limit of human perception, a smoothed-over version of a much more chaotic reality. Think of a lens not as a passive window, but as a tool for forced synchronization. If we go back to our mad couriers with their stopwatches, we realize that the couriers taking the path through the center of the lens have the shortest distance to travel. In a vacuum, they would arrive way ahead of everyone else, their stopwatch hands pointing in a completely different direction than the couriers who took the long way around the edges. They would never agree, and you would never see a clear image. You just see a blur of mismatched phases. The lens is engineered to fix this. It is thickest in the center for one very specific reason, to force the couriers taking that shortcut to trudge through that jello longer than anyone else. While they are struggling through the thickest part of the glass in the middle, their internal stopwatches keep ticking away. Meanwhile, the couriers going through the thin edges of the lens, the ones taking the long way around, breeze through the glass much faster. The entire genius of a lens is that it precisely balances the polite but delay maturité of the glass with the distance of the path. It makes the travel time for all possible routes, the long detours through the edges and the slog through the center, exactly the same. The lens artificially realigns the hands of their stopwatches so that at one specific point behind the glass, every single courier, no matter which path they took, arrives with their stopwatch hand pointing in the exact same direction. When the system forces light to trudge in just the right places, we get focus. We get that perfect bass ringing unison where millions of high voices finally hit the same note. This is how a telescope captures a distant star, or how your eye focuses on these words. It's not a miracle. It's a calculated manipulation of delay. Lenses have no other choice. They are built from the same atoms and governed by the same physical limits that have been measured and verified for over a century. They do not operate on a different set of laws than the mirror. They just exploit the noise rate of the universe to create an artificial harmony. Once you realize that even a high-precision instrument is just a way of managing a swarm of mad couriers, the story naturally has to take another step. This is no longer just a clever way to think about optics. It is a serious statement about the bedrock of reality, and it's here that we cannot avoid the most important question of all. In science, you can tell an incredibly convincing story. You can build beautiful metaphors about mad couriers, jello pools, and stadium choirs. But if you cannot measure something in the real world, if you cannot bring it back to concrete numbers, it remains just a story in the end. If photons truly explore every possible path in the universe, if they really are sensing the entire environment before they decide where to land, then that effect must leave clear, unmistakable traces in specific experiments with real equipment and real numbers. Remarkably, we do not need a super collider or a trip to a black hole to test this. As early as the mid-20th century, physicists began to put this mad courier theory to the ultimate test. They looked at the anomalous magnetic moment of the electron, a tiny, flickering property that should, in theory, be influenced by every single hidden path a particle can take. When the calculations were first done on paper using the principles of quantum electrodynamics, the result was a number of staggering complexity. But when those numbers were compared to actual measurements in a lab, the result was clear. They matched to more than 10 decimal places. To give you a sense of what that means, it is like measuring the distance from New York to Los Angeles and being off by less than the thickness of a single human hair. This was not a fluke. It was not a coincidence. This precise match is nature's way of nodding in agreement. It shows us that this is not just a theory in a was or bien, it's nature in the way we use the word in everyday life. This is the deepest, most accurate description of reality humanity has ever achieved. When you look at the world this way, you realize that the laws of optics, the things your teacher drew on the board, are not absolute commands. They are more like a horizon. They are the result of an asymptotic process where billions of chaotic possibilities cancel each other out until only one consistent path remains. There is no cosmic police officer Intriope standing at the mirror telling the light where to go. There is only the consistent structure of probability and time. This often disappoints people at first because it offers no simple, solid thing to hold on to. There is no solid beam of light, only a surviving echo in an ocean of noise. But to me, this is where the real beauty lies. It shows that the limits we encounter, the speed of light, the way a lens focuses, the way a mirror reflects, are not signs of a restrictive or stingy universe. They are signs of a profound and coherent structure, a structure that allows us to see, to think, and to exist in a world that makes sense. So, why does the light reflect that way? Because if it did not, the universe would no longer be itself. Causality would break. The shared order of events that all observers accept would dissolve into a tangle of contradictions. The universe we know, the one confirmed by over a century of precision measurement, operates by ensuring that out of the infinite chaos of possible paths, only the most consistent story survives. Quantum electrodynamics does not say, do not dream. It says, dream honestly. It tells us that while a particle might explore the entire universe in a heartbeat, it ultimately obeys a harmony that we can understand and measure. It reminds us that the best imagination is one that respects reality, because reality itself is far more imaginative than anything we could invent. In the end, we are slower than light. We are bound to the ground watching these photons perform their impossible dances at 299,792,458 meters per second. But that does not make us insignificant. It means we are part of a vast, interlocking structure where every piece has its role. When you understand why the mirror reflects your face the way it does, the limit ceases to be a barrier. It becomes a window. It's a reminder that we live in a world where everything has a reason, even the parts we cannot see. And when everything settles, I do not find myself standing before a wall of confusing math, but before a clearer picture of our place in the cosmos. We see the world not because it is simple, but because it is a beautifully tuned chorus of infinite possibilities. And when you reach that point, not by moving through space, but by moving through thought, you can smile very quietly to yourself and say, so that's how it works. If questions like these make you want to pause and think more about the universe you live in, please subscribe so we can keep digging deeper together. See you in the next conversation, where I want to join you in asking more seemingly simple questions that always take us very far.